All right. We good? Okay, so welcome to Astronomy Clubs of New Jersey. We're back on site indoor this time because it was raining rather hard outside. And as much as I love being outside, a tent is not quite enough. So while we're waiting for, I heard out there that we have a few people still parking and making their way indoors. Want to welcome you guys who are not only here, but also online in our chat room because we do live stream these to Twitch and YouTube. If you are on Twitch or YouTube, hit those like and subscribe buttons. They're completely free ways to actually support what we do and let people uh, see us a little better on those algorithms. You can also check us out on our website, uacnj.org. That's where you're going to find a list of all our upcoming talks we've had in the past, uh, all our telescopes that we have here on site, as well as a list of our member clubs because we are a club made up of other clubs. And trying to connect people to their local astronomy club is a major thing besides outreach of what we do. Angry speaker. um, you can also check us out on our social media pages, Facebook, Instagram. We have our Discord channel if you want to share, which is a great place to share those uh, astrophotography photos, as well as ask questions, get answers about your current setup or what setup you might be looking to buy. I would love to see a little more chatter in there. I do try and keep up with that. Um, you can also we have a little museum and gift shop here, but you can also check us out on our online store, which is store.uacnj.org. It's linked on our website. Uh, we have some online only exclusives there, so go check that out. So since I've seen that people have finally, uh, I'm getting a nod that people are finally parked and mostly here and on their way in. Uh, Welcome here. If you need to use the bathroom, that is the porta potty. Unfortunately, outside, it is illuminated by red. You did fix that, right, Chris? Cool. He said he's fixed it. Um, you. We also have the museum area and gift shop, which you walked in to get to the little tiny indoor lecture area. Uh, so with that, tonight's presentation is the life of stars, correct? You do a number of them, so I have to double check sometimes. With Walt Windish. Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1985, just in time to see Halley's Comet. Walt's a member of the North Jersey Astronomical Group and the Rockland Astronomy Club. He's been volunteering here at Jenny Jump for much time.
No comment.
And with that, here's Walt.
Well, thanks a lot for braving the rain and coming on out. This is the first time I've ever sat down doing a presentation. It's a little weird, but I don't want to get in anyone's sight lines. As Kim said, what I'm going to be talking about is the life and death of stars, which is a good time to change the slide. And I've done this talk a number of times, and there's just a lot of stuff to talk about. So what I do is I usually concentrate on different areas at different times. And tonight I'm going to be focusing a little more on how astronomers use the Hertzsprung-Russell diagram. And I'm also going to be talking about neutron stars, which fit in between a normal star remnant and a black hole. So we're going to spend a little extra time talking about neutron stars and magnetars and all that good stuff. But first, I just want to go through some simple science that you can use when you're out looking at a scope on a clear day. There's a difference between apparent and absolute magnitude. Apparent magnitude is how bright the star looks in the sky. And we assign numbers. The lower the number, the brighter the star is. And, that used to be real important to people like me before we had GPS telescopes and scopes that you just push a button and they skew over. What we used to do is we'd have to star hop. We'd have to find a bright star and then look for a little dimmer star and hop from star to star until we found the object that we were looking for. And still, when you look up in the sky, you look for different magnitude stars and it tells you how clear the sky is, how good the scene is, and that gives you an indication of what you'll be able to look for. Then there's absolute magnitude, and that's important for doing science. Right? We need to know if two stars were next to each other, how bright they would actually be, not how bright they appear to be. So if you look at this analogy on the cars, the first one on your left, you'll see that two lights that are identically bright, and one is a mile behind the other, obviously the A is going to look brighter because the apparent magnitude is greater. Now if we have two cars, A and B, that are the same distance, and A's headlights are brighter because he has a brighter bulb in there, then that's absolute magnitude. A is absolutely brighter than B. They're both at the same distance. And so what scientists do is they calculate the luminosity of a star at what they call 10 parsecs, which is about 32.6 light years away. So they equalize all the stars as if they were 32.6 light years away. And that is the apparent absolute magnitude. So here's a list just to give you a feel for apparent magnitudes. We see that a full moon is negative 12.5. That's very bright. Venus comes in at negative 4.4, Sirius negative 1.5. The limit of binoculars is about magnitude 10. And the limit of the Hubble telescope is a magnitude of 30, which is, you're really looking deep into the sky now. And the new James Webb scope can see to about 34. At least that's the stated magnitude. In the case of James Webb, it's just how much time do you have. The longer you point the James Webb scope at an area, the deeper and deeper into space you're going to see. But practically, they say it's about 34. So this system of magnitudes dates back about 2,000 years to Hipparchus. Some say Ptolemy, where they used to say the brightest star was a star of the first magnitude. And then as science got more and more precise, they tried to adopt that already existing scale into modern science. And it's become a little clunky, as you can see, with stars in the negative, but we make it work, and it's still in use today, and I guess that's not going to change. You know, the absolute magnitude of Sirius, a star that's easy to see in the sky, is 1.4, and that's compared to the absolute magnitude of our sun, which is 4.83. So if the sun was 36 parsecs away, it would be a 4.8 magnitude. So there's a lot of stars you could see that are brighter than the sun when they're all equalized to 10 parsecs away. One other thing we can talk about is the electromagnetic spectrum. And that's interesting because electromagnetic spectrum covers everything from radio waves to gamma waves. And we can only see this little tiny sliver. That's visible light. Everything else is beyond what we can see. But we can equip telescopes to see those other wavelengths. And so some of the really cool and beautiful photographs or images that we see of nebula and the like are combined visible and other spectrum. And they give false color to, like, most commonly infrared and ultraviolet. They'll give false colors, and you'll see more detail than originally you could see with even a really powerful telescope. Infrared has a habit of cutting through dust, and so it really helps you see through dust, where obviously in visible light, the dust is just, that's it. It's blocking the star. You might be able to see a little bit of light shining through. So what do you see here? Hopefully you say nothing. There's no pattern, there's no data, it's just a random distribution. And when there's some relationship between the dots, we say a pattern emerges, and we should see some kind of correlation in one way or the other. So two wild and crazy astronomers by the name of Hertzsprung and Russell, they took a major step in our knowledge of stellar evolution. They discovered that when the luminosity of a star is plotted against the temperature, we get a graph like this, and we see something called the main sequence, which I'm going to explain, and an area where giants and supergiants hang out, white dwarfs. So we see some definite distributions when we look at absolute magnitude, which is also luminosity. And by the way, the sun is set at 1, so the luminosity of our sun is 1, and everything's plotted against that. And then we also see the temperature, also known as the spectral class. So the stars within the same region share similar characteristics. And that's like the periodic table of elements. But the difference is the periodic table of elements gives you information about the elements that's static. But a star can change its position on the HR diagram as it evolves. Most of the stars will spend most of their time on the main sequence. Once the radiation trying to force the size of the star outward, and the gravity trying to bring the star inward, once they come to equilibrium, it's called hydrostatic equilibrium, then the star is stable and it'll sit on the main sequence for most of its lifetime. Our sun will spend about 10 billion years on that main sequence, but then it'll move off. As it runs out of hydrogen, it starts to get a little weird and starts moving up into the giants and the supergiants, as we're going to see. There's a couple different, this kind of looks like a dot matrix printer, and they've been some really nice computer graphics formed of these of the HR diagram. Here's another one that just, it adds a little color to it. And we can see our sun. See our sun right here in the middle, right in the yellow portion, very average. It's got a luminosity of 1. Nothing out of the ordinary with that star, which is a good thing. It helps us live here. So here's another one. Oh, this is a table that shows the size of the star versus its projected lifespan. And it's very interesting to see that the larger mass, the shorter the life. So a star that's 60 times the mass of our sun is going to live about 3 million years. And that's going to be a very bright, it's going to burn itself out quickly. You get down to one solar mass, which is our sun, it's about 10 billion years. And the smallest stars, the brown dwarfs and so, are projected to live for trillions of years. And obviously, since our universe is only about just under 14 billion years old, we haven't seen any of these stars die because we're projecting them to live for a trillion years. This is my favorite HR diagram. It's got lifetime data on there. You can see lifetime of each of the, and the higher up you go, the shorter the life. So if there were no new stars being birthed, you would expect to see this diagram shrink as the hottest stars fizzle out. But as we know, stars are being born all the time in places like the Eagle Nebula, the Orion Nebula. Those are birthing places of stars. So we always have a new supply of stars. Oh. And here's another. This is from Astronomy Magazine. I think they did a really nice job on that. It kind of gives you an idea of the size. It's not the scale, but still it gives you an idea that the longest life stars and the coolest stars are all the way over on the bottom right. And remember, this is luminosity. So as the star of the same temperature gets bigger, it's brighter only because there's a whole lot more surface area. And so we see the smallest stars down here. And by the way, white dwarf is where our sun is going to end up, and we'll get there. The sun is on here somewhere. Here's our sun. Again, here are the hottest stars and the brightest stars are the largest stars. So we go from hot to the coolest stars, from the smallest or less luminous given any temperature to the most luminous, which are larger stars. Yeah. Those are different class of stars based on temperature. So our star is a G star. And so the O stars are the hottest stars. I remembered that for "Oh, be a fine girl, kiss me." You probably don't teach that in school like that anymore, but that's how I remember the spectrum. So let's just talk about the life of our star for just a minute. And stars up to about 5 to 8 times the size of our sun. You know, a huge cloud of dust like we see in the Eagle Nebula or the Orion Nebula starts to condense because of the gravity. And as it condenses more and more, it heats up. And it becomes hotter and hotter and becomes a protostar. The particles are brought close enough by gravity that they start to fuse, and the star begins to shine. And hydrogen atoms fuse together to make helium in a process known as fusion. It's nuclear fusion that creates the energy that powers the stars. And as I said already, once the star stabilizes in hydrostatic equilibrium, it becomes a main sequence star. It's going to be stable, and it's going to live most of its life sitting there on the main sequence. And that's a delicate balance between gravity that wants to collapse the sun and fusion radiation that wants to just blow it apart, that just wants to exert outward force. But at some point, our star is going to run out of hydrogen or run low on hydrogen, and there's going to be helium in the core. There'll still be some hydrogen burning on the outside. And as helium's fused, it creates more and more energy. It takes more energy to fuse helium than hydrogen. And so our star is going to get hotter, and it's also going to begin to expand. And this time, it'll move off. I have a better diagram later, but it'll move off the main sequence, and it'll become a red giant, a subgiant, and then a red giant. And we'll be inside of it at that point. And then it'll get hot enough to fuse helium atoms into oxygen and carbon. At carbon, it stops and blows off its shell, as we'll see in a little while. So that's the HR diagram. It classifies stars, but it also shows their movement within the diagram in accordance with stellar evolution. So let's look at a little applied science using this. Let me just see. Here's a gorgeous image of a globular cluster. It's known as NGC 6397. It was taken by the Hubble telescope, and globular clusters are generally very old spherical clusters in the outer regions of our galaxy and in the outer regions of other galaxies as well. There's about 150 globular clusters around our galaxy, and they're fun. There's a fun object to see with telescopes. You can see some of them in little scopes. Some you need larger scopes to see, but they're always a tightly packed sphere of different stars. And in our Milky Way, like in most spiral galaxies, you'll find these globular clusters around the galactic halo, around that middle fuzzy part. So NGC 6397 is one of the closest globulars to Earth. It's about 7,800 light years from us. And when I say something's 7,800 light years from us, it means that it took light 7,800 years to reach here. So we're actually looking back in time. We're looking at how that globular cluster looked almost 8,000 years ago. And when we see things that are you know, a billion light years away, you're looking back in time. So the telescope is a time machine. It's showing us what objects look like in the past. And that is great for cosmologists, because if they want to see the evolution of a galaxy, they can look at very old galaxies and see how a younger galaxy looked and surprising, there's less difference than were originally thought. Now this globular has about 400,000 stars, and they're thought to be old, over 10 billion years old, and roughly the same age, which is very interesting. So a writer wrote into Astronomy Magazine. I love this question, and it shows how we can use the HR diagram to do some science. So he says, the globular cluster, this globular cluster, is 7,800 light years away. If the light we observe is 7,800 years old, what measurement is used to determine the cluster is 13.4 billion years old, which is the estimated date of this cluster, over 13 billion years old. Right? So to start with, astronomers assume that all the stars in the globular cluster are the same age. There's no new stars being born. There is no nebulosity to it. So they're about the same age, and they've been aging together. Now remember, we saw that this is the main sequence, and those are the stars in hypostatic equilibrium. We also know that the brighter stars die first. So if we have a stable population of stars, what should we see? We should start seeing this main sequence getting shorter, right? As stars leave the main sequence to become supergiants, the brightest and the youngest will disappear, and you expect that over time. They'll use their hydrogen fuel, they'll burn the helium, they'll get hotter, and again they will they'll turn into giant and supergiants, and then they will either go supernova, or they'll throw off their outside ring, as we're going to see in a little while. And all the white stars are the smaller stars, like our sun, still burning hydrogen. So as more stars mature, they enter what's known as the red giant branch. So as they are done burning their fuel and they start burning more exotic elements, they take a turn and they go up towards that part of the HR diagram, just as our sun will. And that's known as the main sequence turnoff. So we can use turnoffs to figure out how old the cluster is. Remember, we're doing an HR diagram of a cluster of stars, not of the entire universe. So we're looking at a specific population, and we're looking at the distribution of stars, just as the HR diagram has shown us. The temperature, which is also color, and the luminosity of them, and we plot them out. And we see, since O stars live 1 million years, some a couple million years, and our sun lives 9 to 10 million, you look at where the cutoff is, and it gives you a very good idea of the age of that cluster. And again, the red stars can live 50 to 60 billion years plus. I've heard numbers as high as 1 trillion years. We don't know for sure, but they certainly live an awful long time all the way down in that region. So with 400,000 stars in that cluster, we've got a lot of data points. And by looking at where the main sequence cutoff is and how far the stars have turned off, have evolved, astronomers can estimate the age of the globular cluster. So this HR diagram is very useful for determining the age of clusters and other objects. It gives us a lot of insight. So the age of this cluster is estimated at 13.4 billion years old. That compares to 13.61 billion years for the Milky Way, and about 13.7 billion years for our universe, plus or minus 200 million. So that gives us a good idea of the age of this cluster. So I'm going to try to give you an idea of just how much these stars will vary in size. And I'm not starting off with a star. What does anyone know what this is? Jupiter. Yeah, even my 2-year-old now can see Jupiter. Matter of fact, she was walking on a floor, and there was a knot in the floor, and she said, "Oh, great red spot." She's definitely into Jupiter. But About 28 years ago, a comet Schumacher-Levy broke into about 21 pieces and struck Jupiter. And then Jupiter rotated so that we could see the damage left behind by the fragments of Schumacher-Levy. And the reason why I'm showing you that is that these bits here are about the size of the Earth. So we can see the scale of Earth to Jupiter, and that's our starting point for looking at the size. So the moon is about 2,100 miles in diameter. The Earth is 7,900, and Jupiter is 86,881. And the Sun is 864,000 miles. So it's about 10 times the size of Jupiter. And the Sun is 10 times the diameter, but 1,000 Jupiters can fit into it. So 1,000 of these can fit into our Sun. So how does the Sun stack up to other stars? Okay, well, there's our Sun way over. He's not feeling all that big anymore. These are red giants, supergiants. We've got Arcturus is about 21.9 million miles. That'll take you 2/3 of the way to Mercury if it was where our Sun is. It's the brightest star in Bootes, so it's called Alpha Bootes. You know, stars are named. Some stars have special names, like Mizar and Alcor, but they all have a designation of a Greek letter and the constellation name. That's the official name of the star. And so Alpha Bootes tells you Alpha is the brightest star, and Bootes is the constellation that you can find it in. And Arcturus is an easy one to find because if you look at the Big Dipper, there's the arc of the handle, and you follow the arc to Arcturus. The first bright star you will see is Arcturus, and then you can speed on to Spica, which is the next bright star. Well, now Arcturus isn't looking all that big anymore. The red giant Betelgeuse has a diameter of 765 million miles, and it's about 700 light years away from Earth. If it were where the Sun was, we would be inside of it, and Mars as well. We'd be inside, and that's basically what's going to happen to us when our Sun turns into a red giant. But we'll have boiled off the face of the Earth way before then. You can fit 1.3 million Earths inside our Sun and 700 million suns inside of Betelgeuse. So we're getting into some big territory here. Betelgeuse is designated as Alpha Orionis. It's the brightest star in Orion, and it's a relatively cool star compared to some of those blue guys all the way on the left side. But it's so big that it accounts for the brightness. It's the size that's really accounting for how bright that star is in the sky. It's also the ninth brightest star in the sky, and it's part of the winter triangle of stars, along with Procyon and Sirius. Red supergiant Antares, this guy here, is 604 light years from Earth and 700 times the size of the Sun's diameter. But its overall density is less than 1/1,000,000th of the Sun. So this star has gotten so puffed up, it's not very dense at all. It's big, but 1/1,000,000th of the density of the Sun. And it's Alpha Scorpii. It's the eye of the scorpion that if the skies were clear on a sunny summer day, you could see it just looking out to the west, to the southwest. It's a very easy object to see, and I hope you come back in the summertime when you can really see, because it's amazing. If you look into Sagittarius and Scorpius, you're looking right into the center of our galaxy, and there's so many objects in there to see. It's amazing. It's the 15th brightest star in the night sky. Its exact size is uncertain, but it would reach further than Betelgeuse. And there's a big one. VV Cephei is one of the largest known stars. Its size is uncertain, but it's estimated 1,050 to 1,900 solar radii. Its photosphere or outer shell would reach almost to Saturn, and it's 5,000 light years away from us. And I was talking about strange objects about 3 or 4 weeks ago, and someone asked me what was the largest star, and I just couldn't. They get the weird names when they get that big, and I couldn't think of EV-C5. That's one of the biggest. And although we're constantly finding new stars, the biggest star we know of is YU Scuti in the constellation Scutum. It's about 1,700 times larger than our sun, about 1.48 billion miles, but it's only 30 times the sun's mass, and it would also come very close to Saturn's orbit. And so while UI Scuti and VV-C5 are the largest stars, R136A1, great name to remember, is currently the heaviest star in the universe. It's located in the Large Magellanic Cloud, which you have to go south of the equator to view. It's approximately 165,000 light years from us, and it's a member of a rare class of hypermassive stars. And this one weighs in at more than, it's somewhere between 170 to 230 times the mass of our sun. It's a pretty heavy star. And a lot of these that are less massive of the sun, I mean, this is like probably fall right through it if that were possible. The title of the brightest star in the universe, in terms of intrinsic luminosity, absolute magnitude, belongs to the luminous blue variable star in Eta Carinae. It's situated about 7,500 light years away from us in the constellation Carinae. Eta Carinae outshines our own sun millions of times over. And again, to see that one, you have to go south of the equator. So as we've said, a star's position on the HR diagram shows where it is in its lifespan. And this is a simple diagram showing the sun moving off of the main sequence when it starts burning helium. It becomes a subgiant, and then it starts burning helium, and then becomes a red giant. And at some point, the sun will blow off its outer shell. About half of its mass will be blown off into what they call planetary nebula, which will stick around for 50 to 70,000 years and then dissipate. And what's left is a white dwarf. And this shows that the star it gets hotter, and then it starts cooling, and it'll cool for billions of years. And that's the life of our sun. So what's left behind? Well, this is very similar to what the sun will leave behind. There's a white dwarf. It's about magnitude 13. This is the Ring Nebula in Lyra, and we can see it directly over our heads in the summertime. And then this is the gas. Half of the mass of the star has been blown out into this gas envelope. Again, heat's not produced by nuclear fission at this point, but just by the super high density of the star. And remember, I spoke about different wavelengths giving you different information. So we take a picture of this in the infrared and combine it with this visual photo that the Hubble gives us, and look at the difference. Look at all the extra information. You could almost feel this shock wave as the red giant expanded and left its shell, and then collapsed back into a white dwarf. I guess that takes about 100,000 years, and just leaves the white dwarf. But the infrared shows us that there's other gas here that's hot enough to be detected, but not by the naked eye, not by the in the visible spectrum. You have to go to infrared. This is the Dumbbell Nebula, and I'm not going. I've spent in past talks. I've spent a lot of time talking about these. I want to get to neutron stars this time. But I do want to show you a couple examples of what it looks like. Our star, our sun, will not die a violent death. It will not have a supernova explosion like the explosions that leave a neutron star or a black hole in its way. It's kind of peaceful. It's still going to wipe us out, but as far as star evolution is concerned, it just expands. It leaves a very pretty shell that lasts for 50 to 70,000 years, and then half of its mass is a white dwarf, and that stays for billions of years. Actually, the planetary nebula phase only lasts about 30,000 years. I just looked at my notes, and this is about 1 light year wide. So that's pretty big. It takes light a year to travel from here to here. It's a pretty big object. This is a pretty one. This is the Cat's Eye Nebula. It's formed by a star very close to our suns in mass, and it has like 11 plus bubbles of gas surrounding it, which is very unusual. Scientists are still trying to figure out what caused that. This is like cutting an onion and looking at the rings, but each of these rings is really an entire bubble surrounding the nebula. And there's all kinds of different theories on how it's caused, from magnetism to just the star pulsating out mass. But it's a surprise that astronomers are still working at. It looks like if it was pulsing out mass, it would have had to pulse out every 1,500 years or so for at least 11 rings. This planetary nebula is nicknamed Hubble's spirograph for the obvious reasons. It's about 2,000 light years from Earth. So all of these planetary nebulas started out similar to our sun. Then they became red giants, and then the outer atmosphere drifted off, and what's left is called a white dwarf, and is so dense that approximately half the mass of the sun is packed into the size of Earth. So half of the sun's mass is packed. That's very, very dense stuff. So stars with less than 8 solar masses are sometimes called dwarf stars because they leave behind white dwarfs. So right now the sun can fit 1,300,000 planet Earths inside of it. So imagine half of that sun, half of that mass, in a space less than a millionth of the space. That's a very dense. So 650,000 Earths packed into the size of the Earth. Unbelievably dense. So here is a star of 1 solar mass, which would be our sun, and we've looked at how it turns off the main sequence and heads down the red giant branch, and then sheds a gas shell as a planetary nebula and leaves a white dwarf behind. These much larger stars, 15 masses, actually from 10 on, they go beyond the carbon stage, and they keep burning different elements. They keep burning till they get to iron. Once iron hits the core, iron requires more energy. Up to iron, energy is produced. When you hit iron, it requires energy. And so we have automatically the star just implodes and then goes out into a supernova explosion. So as soon as iron builds up in the core of a high mass star, there's catastrophic consequences almost instantly. The process of fusing iron requires the star's core to use energy, which causes the core to cool. And this causes the outward pressure to go down, which speeds up the gravitational collapse, and that's why it implodes. It goes in first, and then it explodes. It causes a chain reaction. Core collapse, iron fusion rate increases, pressure decreases, the core collapses faster, but it happens within minutes, the whole catastrophe. And for a brief period of time, the light generated by one star as it's exploding in a supernova outshines an entire galaxy. And you just can't capture that on an image. But there's a supernova, and it's so bright that it's outshining the entire galaxy here. This is called the Tarantula Nebula, and supernova 1987, which was a big deal. It went supernova closer to us, closest enough to us that we gathered information that we could never have gathered before. Nobody has seen a supernova during the daytime in modern times, although Tycho Brahe and Johann Kepler observed naked eye supernova in their time. No one in modern times has. This is a picture of the supernova 2 weeks after the explosion. And again, so we can get to the neutron stars, I'm just going to go quickly through the supernova. But these are some pictures of the 1987 A rings showing the shock wave coming out and hitting the rings left behind. Over a number of years, you can see from 1994 to 2016, the shock wave from the supernova explosion came out and mixed with the with matter that was ejected by the explosion. And so slowly but surely, we could see how the matter lit up as the shock wave came and better intermixed with it. This is an artist's conception of what a supernova looks like, with the explosion and the shock wave. And what's left behind is a super dense core known as a neutron star. If the star is under, say, 60 to 80 times the size of our sun. If it's greater than that, we expect that it'll leave a black hole behind. So what's left behind in that interim between 8 solar masses and about 60 or so solar masses is a neutron star. And neutron stars are not rare, but they're weird by earthly standards. And as I was thinking of that, I realized that what's really weird is the Earth. Because when you look out into space, we see neutron stars, we see black holes, we see all what we call exotic objects, but we don't really see another Earth. And so this is normal, and it's really Earth that's abnormal. It's very unique. So when I do a talk called Strange Objects, they're really just amazing objects from an earthly point of view. So strewn across space are dead stars, the remnants of supernovas, white dwarfs that are no longer burning fuel. They're just cooling down, and their heat is formed by the intense gravity that's pressing down on them. So some of those stars are neutron stars. And a neutron star can have a mass greater than our sun in the space of an area the size of New York City, about 12 miles. So if you thought a white dwarf was dense, a neutron star is really cranks it up. The sun weighs 333,000 times more than the Earth. So imagine half that, the mass of 166,000 Earths packed into a space the size of Manhattan. It's 1 trillion times more dense than our sun. The black hole is denser than this. Yeah, which is amazing. Light can still escape from a neutron star. Radiation can still escape directly from this star. But the mass is so tightly packed in a neutron star that a teaspoon, at least a NASA spokesman has said, a teaspoon of neutron star would weigh more than Mount Everest, which I just can't imagine. So white dwarf is dense, but this really cranks it up another notch. And if that's not enough, they spin around multiple times per second. The fastest one was clocked at a rate of 716 revolutions per second. I mean, I can't even imagine that. And Manhattan spinning around 716 times a second. Unimaginable. Um, Theoretically, they can spin as fast as 1,000 to 1,500. We haven't observed that yet. We've observed them over 700 revolutions per second. And what you're looking at here is an artist's rendition. It's not a Hubble's shot, but it's an artist's rendition of a fairly rare object. It's called an isolated neutron star. It's a neutron star without any supernova remnant, without the gas shell or without any remnant of a supernova, just a stripped down neutron star. And we just discovered one. That prompted this artist's drawing. We found one in Ursa Minor, only about 250 to 1,000 light years away, so really close to us. We have not confirmed beyond a doubt that this is one of those neutron stars. But if it's confirmed, it'll only be the 8th isolated neutron star that we've discovered. So they are pretty rare. That would only be the 8th one. The 7 other neutron stars were collectively known as the Magnificent Seven. So they kind of closed the door. Now they found an 8th. So what do? Well, the working name for this is Calvera, which was the bad guy in the Magnificent Seven. So there's Calvera. Hopefully he gets confirmed as a isolated neutron star. But here's an example of some more common neutron stars. This is very rare, and up to a few months ago, I had not known about that, an isolated neutron star. So this is a Hubble photo of my favorite neutron star hiding in a nebula, in a supernova remnant. It's a mosaic image taken by Hubble. The largest, at the time, it was the largest ever taken of the Crab taken. 6 light year wide expanding supernova remnant. And what I really like about this, you can see this in a telescope, but Japanese and Chinese astronomers saw this in 1054 and recorded it when it went supernova. And they recorded that they could see it during the day. So it's so cool to look at the telescope and see this, which really in a telescope it looks like a faint, cloudy, fuzzy object. But to think that there were people on this planet that saw this thing go supernova and they could see it against the blue sky, and that they recorded it for us to find out about it. It just blows my mind every time I think of it. And I can't help thinking of those astronomers every time I look at the Crab Nebula. About 1,000 years ago, not even 1,000 years ago. And so as I said, it's 6 light years wide. So this supernova remnant has expanded 6 light years in those 1,000 years. And again, it takes light 6 years to go from here to here. That's a pretty big object. There's a rapidly spinning neutron star in the middle of it. And it's the neutron star that's illuminating this entire remnant. The blue light comes from electrons whirling at nearly the speed of light around magnetic fields that are caused by the neutron star. And the neutron star, like a lighthouse, ejects twin beams of radiation. It rotates 30 times per second. So this particular pulsar, it's a neutron star that gives out energy in pulses. It looks like pulses. It's called a pulsar. It's not really giving it out in pulses. It's giving out continuous energy. It's like a lighthouse. When you look at the light, you only see that light for a second, and then it goes away, and then it comes back. So it looks like pulses, but it's continuous energy that's coming in, and it's just spinning so fast that we're seeing pulses. Some spinning so fast that we call them millisecond pulsars. So this star, this pulsar is rotating so fast that if you marked a spot on the equator of that star, it would be traveling at about 3.4 million miles per hour. Neutron stars are the only stars that we know of that can rotate this rapidly and not fly apart. And it's because they're so dense. Here's a fairly new image from August of 2022. It's still the Crab Nebula, but it has 3 different spectrum to make this. The visible light from the Hubble Space Telescope is the purple that you see. X-ray light from Chandra X-ray Observatory is blue, and infrared light from the Spitzer Space Telescope is in red. So this is a great picture of the Crab pulsar. It's a type of neutrons. Not all neutron stars are pulsars, but all pulsars are neutron stars. And you can see the pulsar itself as the bright spot in this picture, in the gaseous swirl. Some neutron stars, such as the Crab pulsar, emit radio waves and other forms of radiation. And because they spin so quickly, as I said, they seem to send out pulses of energy. And they're not pulses, they're just continuous energy that we're seeing as that look like pulses because of their rotation. The distinguishing mechanism in a pulsar over a regular neutron star is that the pulsar has a very strong magnetic field that's about 30 degrees off the rotation axis. And this misalignment not only creates the energy, it also slows the pulsar down a tiny percentage each year. So they get slower and slower. And the magnetic field traps and accelerates all charged particles and energizes them to millions of volts. It'll take about 10,000 years for the neutron star, this pulsar, to slow down by half. So about 10,000 years it slows down by half. And eventually the X-ray radiation will disappear, and all you will be left with is radio signals coming from it, radio waves. It'll be a radio pulsar, as they call it. So if anyone heard my strange object talk a couple of weeks ago, you'll see that the explanation for a lot of the strange objects, one of the possibilities is usually some kind of alien intelligence, at least in some of them. And it's always something that we should consider if it looks like that. But the nickname for these pulsars when they were first discovered in 1967 was LGM, Little Green Men, because the pulse of the energy was so consistent and so even that it was thought that it could be a sign of intelligent life. And so they started out as Little Green Men. Since they were discovered in '67, we've discovered about 300 of these pulsars. But only two, the Crab and the Vela, emit radiation in the visible portion of the spectrum. The others, you have to use the special instrumentation aboard the Space Telescope or on the ground. Here's an artist's rendition of another common neutron star configuration. A neutron star with a companion star that it's cannibalizing. See how we're doing. Oh. This one happens to be the binary star system, and it's got a, PSRJ 1023, etc. It's an interesting system because it has jets that are so powerful, scientists were surprised because they thought only black holes could produce that type of relativistic jet. And when you hear the term relativistic jet or relativistic something, what it means is that the particles in this jet, or the neutrons within another object, if they're talking about that, are moving close to the speed of light. So when you hear the term relativistic, the particles are really moving quickly. And so neutron stars and black holes are sometimes found in orbit with some companion star, and there's usually an accretion disk that is forming as matter is being sucked off the other star and then being sucked into the black hole or the neutron star. Yeah. Yeah, gravity. Exactly. And again, these relativistic jets are shooting out all kinds of energy. So this was a surprise. Neutron stars sometimes show faint jets, often no jets at all. But to have one this strong is really a head scratcher, and it will be studied quite a bit in the years to come. These jets were only discovered in 2013, 2014, right around there. So we're going to look at one more type of neutron star, and that's a magnetar. A magnetar, a typical neutron star has very strong magnetic fields, about trillions of times that of Earth. A magnetar ramps that up 1,000 times more. A magnetar has a magnetic field that's about 1,000 times stronger than the average neutron star. So we're talking about an unimaginably strong magnetic field. It's a special type of neutron star. Just as a pulsar has its own name, a magnetar's got its own name as well. And since the crust of the magnetar is closely tied together with its magnetic field, any kind of disruption in or small movement in that crust can cause an amazingly strong outburst of energy from a magnetar. According to NASA, a magnetar had a magnetar SGR 1806-20, for anyone taking notes. It had a burst where in 1/10 of a second it released more energy than our sun has in the last 100,000 years. That's a lot of energy. You could definitely toast a hot dog on that. Magnetars are identified as one of the sources of fast radio bursts. That's a current study in astrophysics. I talked about that a little bit in my last talk, but they're not the only. It's been proven they're not the only because, again, they looked at a globular cluster and they found a fast radio burst coming from a globular cluster. And the globular cluster was about 10 billion years old. And a magnetar loses its strong magnetic field in about 1,000 years. So a magnetar could not stay as strong as it is over billions of years. And that's how they ruled out magnetars as a cause of all FRBs. That was one of the reasons. Yeah, we can see them. They don't reach us like a coronal mass ejection that we witnessed from the sun. But yes, we can certainly measure them. I like the way Adam Mann in Scientific America put it. He said a magnetar's magnetic field is so powerful that approaching it within 1,000 kilometers would disrupt your body's nuclei and electrons, causing you to effectively dissolve. That's pretty wild. I mean, it's an amazing magnetic field. So yeah, magnetars become regular neutron stars in about 10,000 years. I think I said 1,000 before. It's 10,000 years. Takes a magnetar to calm down. And again, a neutron star has a pretty strong magnetic field, but a magnetar is about 1,000 times stronger than that. So we have come to 9 o'clock. And I will just review. I've spent a lot of times on black holes before. I wanted to spend a little extra time on neutron stars. So we see in the formation of stars, they all start in a stellar nebula. Gas starts to close in on itself because of the gravity, becomes hot enough to ignite, becomes a protostar. If it's a star that's up to about 6 or 8 times the size of our sun, including our sun, it'll take the top path and eventually will become a red giant, then blow off its shell, which is about half of its mass, and the other half of its mass will become a white dwarf, which is half the mass of the sun packed into the size of the Earth. On the other hand, if it's a massive star, up to about all massive stars will become red supergiants, supernovas, but what is left behind, up to about 60 times the size of our sun, will be a neutron star. And if it's somewhere around 60 to 80 times the size of our sun, plus it's a black hole is left behind. It's an oversimplification, but it's It's true. And you can go on the internet, and I hope you do. I hope you're moved to look up some of this stuff for yourself. You can see all kinds of charts, and they get more and more complex because it's not a simple subject. We see all types of ways of explaining stellar evolution. Here's a picture of an artist's conception of a black hole. Picture of a black hole, sorry. Artist's conception. You never see a black hole, but you can see the accretion disk around it. We've actually been able to see that. And only recently have we been able to see the accretion disk around a black hole and process the data and come up with that. And so, the more powerful our instruments get, the more data we get, and the better our knowledge becomes. And we also dispel some of the myths that we thought, like the little green men of the neutron star. Golly gee, there's actually a natural explanation for it. One thing a black hole does is gravitational lensing. And what that is if there is a very massive group of galaxies, like this one, this is about 5 billion years from light years from us, it will distort space-time to such effect, as Einstein predicted, that an object directly behind it may be seen, although very distorted. And this is a galaxy that's about 5 billion light years behind this very massive group of galaxies, which is 5 billion light years from us. And you can see how distorted it doesn't look like a galaxy, but we can actually see something that's directly behind there that we would not have been able to see if space-time was not distorted by this cluster of galaxies. One of the coolest things that Einstein actually predicted is the Einstein cross. And what we're looking at here is, again, a gravitational lens through a very massive bunch of galaxies, and there was a supernova went off behind it. And we can see the same supernova at 4 slightly different points in time as they took different routes from behind the gravitational lensing mass. And to me, that blows my mind. So that's what I have to say about stellar evolution today. I'll let Kim take it off. Thank you very much.
All right. Thank you, Walt, for another great talk. Thank you all for joining us. So we are going to be having a question and answer session, but we're going to do a brief safety briefing. First off, when we leave, we are using our headlights. We don't want to get run over. We don't want to see anyone get run over. We don't want to have to fill out paperwork for getting run over. I don't think anyone wants to do more paperwork than they have to in real life. Let's avoid the adult responsibilities. Any flashlights we may have, because it is dark and rainy, do keep them pointed towards the ground. We don't need to accidentally blind people. Normally, I would tell you, each of the little sheds you saw when you came in has a roll-off roof and has a telescope. And on much better, less rainy days, we usually would have them open for you to view through the eyepiece, or in some cases on a screen, because we have put a camera where the eyepiece goes. We don't have a visual telescope that can see through clouds. It just does not exist. The first person who will make that will never have to work another day of their life. So someone get on that. But besides that, we're going to do a question and answer session, since we have some questions online, and I'm sure you have more questions here. The first question here was, how did they come up with the categorizing them as if they were all at 10 parsecs away? Meaning the stars, for determining absolute value.
I can't tell you the logic behind that decision, but they had to pick a distance to normalize the brightness of the stars in order to come up with what would be an absolute magnitude.
All right. Question here? I see one in the back.
Hello, Walt. I may have missed it, but what drives a magnetar to being extra magnetic?
That's a good one. The that's a great question, and I'm not sure exactly what that mechanism is that creates the extra the 1,000 times more magnetic. Uh, my guess is it has to do with the spin of the neutron star, but I don't know for sure, so I'm not gonna say.
Uh-oh, he gave you
No,
homework.
that's a great question, and and I was reading up on magnetars, and it's funny that the mechanism was not explained in the reading that I did.
They might not know. So someone needs to do that homework.
Yeah, me.
All right. The next question, and I think they were referring to the chart where it showed the limits of what you can see naked eye, binoculars, telescope,
Hmm.
Hubble. What is the limit of the James Webb Space Telescope on that chart?
The Hubble is about 30. The James Webb is stated at 34, but practically it's really how much time do you have to point at that object. The longer the exposure, the more light you can gather. And they stayed at 34. They could probably go deeper than that if they spent. I don't know how much time you'd have to train the James Webb at a specific object, but at that point you could probably exceed the stated magnitude limit of 34 by devoting more time than is practically that's practical because of all the demands on the telescope. But 34 is the stated magnitude.
I would imagine they would kind of pick a, just like they did for the parsec question, pick a, oh, if we do a 10-second exposure, this is how far we can get on Hubble. This is how far we could get on 10 seconds is probably not the correct measurement, but question. All right, so our next online question is, why are there missing letters? Why choose OBAFGKM and not like ABCD?
Oh my. I'm sure that there is an answer somewhere. A lot of
You're
these
supposed to
classifications.
bring them.
No, a lot of these classification systems are just esoteric, and like the numbering of supernovas, uh, and even do you
Ooh,
have an
we
answer?
have an answer. Hold on.
So some of these classifications go back into the in order to understand like various classifications and stuff in science. A lot of times you have to understand the history of science and the development of it. So the spectra were identified first. And so they were classified in order via spectra before we knew what the objects were and we could assign physical realities. So they were classified by spectra, and then they had to be rearranged in order to, which made them out of order.
Mm-hmm.
But they were originally classified via spectra.
But even then not in alphabetical order because the
Well,
letters aren't adjacent to each
I
other.
don't remember
Yeah,
I don't
well,
remember
I
but
would
that's
imagine
that's
A
great.
is
Yeah,
alpha, B is beta, G is gamma.
I don't
yeah,
I don't
yeah,
remember the level of detail,
yeah,
but the spectra were
yeah.
identified before the physicality of the object
Great.
was assigned to.
Thanks. Yeah,
Neat.
and that kind of goes into the magnitudes that we were talking about, the visible magnitude, where 2,000 years ago they would say the stars of the first magnitude, and then that that system was in use so long, scientists then had to adjust the magnitude scale to fit what they were measuring, and so you have stars that are greater than zero or less than zero, -1, and the like, because they just adopted an old system and lived with it.
Chat's out to get you today. So the next question is, stars are large. Uh, But if you had a vehicle that could withstand like the heat and whatnot of a star, would it read the surface of that star as like a solid, liquid, or gas as far as like landing?
Landing? No, that it would not be.
Well, like if
If you could
if
have
you
a
had the
super
hypothetical
duper asbestos landing gear.
impervious vehicle, like
No, and we've even seen how some of those large stars that are so many that that are 1,000 times the size of our sun, but only 30 times the mass. It's because it's just very gassy. I mean, it's not solid.
okay, so it would be like going through, or not like a boat bobbing on the surface of the lava.
Yeah, you're better off trying a neutron star first. Get it spinning at 30 times a second, and then
Oh,
land
only
on
if you
that.
like those carnival rides that zip you around. I am not that one.
Is that same for Jupiter? Jupiter, you can land either, right?
Right.
Yeah, they actually online chat also had the same question of bouncing off that do we know if our gas giant planets are gas all the way through, or if it has a more solid core?
They have solid cores. Matter of fact, I think Jupiter has a molten core, which is kind of not intuitive, but yeah, it has a solid core, and then inside is a molten core. And some of the gas giants are so cold that you probably could land on them if you had a vehicle that could possibly do that. Just because they're, like methane ice, you'd be landing on something very cold.
Right. Was there another question out here? All right. So our next online question: why does the IR visible shockwave look so irregular on the inner portion? So I think you had the first planetary nebula
Yeah.
that you showed.
Oh,
I
the
for-
Ring Nebula?
I think that's what it was, where you showed, hey, this is what you can see with the visible thing, and then we add on the IR, and here's all the extra stuff you
infrared,
can
yeah.
see.
Yeah.
So you had the ring, and then you had the inner, like, weirdness going on.
Yeah. And so what was the question on that?
Why does that... Oh, go back. Why does this inner thing look more petally instead of like, here's a shockwave, circle, circle, circle?
Well, because the star was expanding, right? Once it was done burning the hydrogen, gravity started to lose out, and the shell drifted out, and so this is really showing the movement that happened. Probably, I'm guessing it was around 70,000 years before it actually collapsed into a white dwarf.
Yeah, I think it was the expecting perfect rings and not like, oh yeah, this is now just wandering away at its leisure.
This looks pretty perfect circle. That's
No, they're talking about the inner.
Oh yeah.
See where
Yeah. Yeah, well, it's been there for quite a while. It's, gas drifts.
now it's just wandering away.
Yeah.
At its leisure. Probably also faster than you would think. All right. Our next online question. Do we have information from things that have completed their white dwarf life portion? Did they just become like a rock?
No, they will continue to cool down. The life of a white dwarf cooling down into a I think they call it a black dwarf is longer than the universe has been in existence. And just like the brown dwarfs, they're estimated to go 50 billion to, I've heard estimates as high as 1 trillion years. Well, the universe is 13.7 billion years old.
So we haven't seen it yet.
We haven't seen it yet.
Do we have like a hypothetical, like this might happen where you now we have a rock? Or is it just like, does it start a different cycle?
Yeah.
Like I said, they have it out for you today.
That's all right. I love those.
They want to give you their homework.
We've seen that it's just super dense matter, but I just don't. It's like an atom bomb goes off in some place on the earth, when is it safe to walk on it? I'm not taking the chance.
All right. Questions? All right. So our next online question, and also because I am getting down to the end, if you guys online have any more questions, do get them into chat. You have the harder or the easier job of typing, but since you have the stream delay, slightly behind real time here, I want to get that out before we get on to the next question. So, and that next question is, how can stars be that dense? Because aren't the density of the elements and therefore the amount of space they kind of take up set?
The gravity becomes so intense that we're not even talking about elements. In a neutron star, the gravity is so intense that it is crushing protons and electrons together to form more neutrons. So it's the atomic structure itself that's being altered, and so it's estimated, and you know, I don't know how we can verify this, but it's estimated that 90% of the core of a neutron star are neutrons, which hence the name neutron star. But yeah, the very atomic structure, because of the intense gravity, is crushed to such an extent that the word element doesn't really mean a whole lot, because you're down to subatomic particles.
Yeah, I think they were kind of imagining one of those YouTube hydraulic press videos where the amount of iron you put into a hydraulic press is going to be the same amount of iron you get after the press does its thing. It's just weirdly shaped now and much flatter. But all right, any questions? I don't even get the crickets from outside anymore. I just get the hum of the server next to me. Come on. Yeah, chat isn't behaving and scrolling. It's stuck.
Okay.
Oh, hold on. Let me check my computer since my phone decided to stick. And my computer's usually not. Oh, yep. Okay. So it looks like we came to the end of our online questions. So I want to thank everyone who's come out here, braved the cold, rainy weather. Everyone who has joined us in chat online. If you are online, do hit those like, follow, subscribe buttons on Twitch or YouTube. If you ever can't make it out here, for anyone here, do check out our YouTube or Twitch streams when we go live. It's a fun thing to do if you have nothing better to do on a Saturday night. Tune in. Do check out our website, uacnj.org. You'll find a list of all of our upcoming talks, which is a great way to find the next talk you all want to come out and see. And with that, everyone have a good night and clearer skies, please. Next week, can I get some clear skies? People stop buying new camera equipment so we don't have to pay the cloud tax. Have a good night.
Thanks, everyone.